modeling of materials. In other words, can we do calculations for designing materials and processes? And I'm going to introduce the different methods of modeling that we have. Okay? And that's what I mean by algorithms, that there are techniques which we use in order to predict what should happen in a material when we do a heat treatment, when we add alloy elements, and so on. So this is a very famous diagram, which is published by 24 in Oxford, where on the horizontal axis we have the length scale, and on the vertical axis we have the people who are working, the subject areas which are working in a different aspect. So first we have electron theory, where we calculate bond energies, the cohesive energy of a crystal, and so forth. And classically that has been done by physicists. Okay. Then we start to talk about atoms and molecules, and that kind of work classically has been done by chemists. When we talk about microstructure, it's material scientists who deal with that aspect. And finally, engineers deal with continuum. They completely ignore the microstructure, but they do other clever things with large structures, very large length scales here. Okay, for example, the 101 tower is an engineering construction, engineering achievement. What I want to show you is that this diagram is now obsolete. Yeah? Instead of having different people doing different things, it is now necessary for everybody to do everything. Okay? So instead of having all those different subjects, we have a new kind of person who we call a materials modeler, who is able to talk about electron theory, or about finite element analysis, or indeed about molecular modeling. And although this diagram has arrows going from electron to atom to microstructure to continuum, we can sometimes even jump directly from electronic theory to very large scale structures. So I'm going to give you examples which demonstrate that we now have a new kind of subject which we call materials modeling, where you forget about the boundaries between physics, between chemistry, engineering and materials. You have to think across the subjects, and there's no restriction in going from electron theory to continuum, or from microstructure to electron theory. All of these are mixed together. So the particular aspects that I'm going to focus on are listed over here. Electron theory, molecular dynamics, thermodynamics. This is a subject which is between thermodynamics and kinetics, finite elements, and neural networks. And I will spend a little bit extra time on neural networks because that is what the organizers asked me to do. Okay? Right, so we begin with the calculation of equilibrium phase diagrams. When I was at university, the way that we thought about phase diagrams is that we do a measurement. Okay, we look at the microstructure, we work out how much alpha there is, how much beta there is after doing a long heat treatment, measure the chemical composition of alpha, beta, and that's just a binary system with, say, copper and zinc. Nowadays, after nearly 70 years of systematic work throughout the world, it's possible to calculate a phase diagram even when you have 20 different elements inside your material and 6 or 7 phases inside the material. So the calculation of phase diagram is now almost a routine subject which industry, you can buy the software which industry uses, or you can download some software from various websites free of charge and do phase diagram calculations. It's only when those calculations don't work, when they don't predict the correct results, that you start to do experiments. But the vast majority of cases you can just calculate a phase diagram. So I will briefly summarize how we do such calculations. So just to define the different kinds of equilibria that we have. First of all, this is what we call stable equilibrium. So I have a ball here, which is in an energy valve here. If I give this ball a small perturbation, that means I shake it a little bit, it will come back to its original position. If I don't shake it, it will stay there forever. That's the meaning of equilibrium. That you look at the system and you see no change happening. Right? Now that doesn't mean that on a microscopic scale there isn't change happening, because you might have an atom jumping in this direction and another one jumping back. It's really a dynamic equilibrium. But thermodynamics means you're dealing with large numbers. Okay? You can't talk about the thermodynamics of one atom. Yeah? It's a whole collection of atoms. And when you look at the whole collection, you see no change happening. Now, in this diagram, I'm assuming that this is the lowest energy state. Right? But we never know whether this is the lowest energy state or not. There might be another minimum somewhere else. So this is what we call a metastable equilibrium, where we have a local energy minimum, and there might be another energy minimum somewhere else. Now, there is really no difference between this state and this state as far as our thermodynamics is concerned. You can use exactly the same laws, equations, etc. So I'm not going to distinguish between metastable equilibrium and equilibrium. This is another kind of equilibrium where if I don't disturb this ball, then there will be no change. It's like having a coin on its edge. Okay? But if I disturb it, then it will tend to fall. So this is what we call unstable equilibrium. And this, of course, is not equilibrium at all, because this ball is rolling down the hill and it's dissipating free energy. Okay? In all of these cases, there is no dissipation of free energy. So this is a completely different situation. It's kinetics as opposed to thermodynamics. Here are two phases, alpha and gamma. They could be ice and water. Okay? And we are plotting the free energy here along temperature. And by allotropic transition, I mean that it's just a change in crystal structure. It's not a change in chemical composition. Okay? Now for this case, it's very easy to define equilibrium. Equilibrium is given by this point here, where the free energies of alpha and gamma are exactly the same. Okay? So there is no tendency for alpha to change into gamma or gamma to change into alpha. And that's why, when you have ice and water at 0 degrees centigrade, they are in equilibrium. They both can exist. So for a pure substance, equilibrium is defined simply by saying that G alpha is equal to G gamma, where G is the free energy. Now, that is not true when we have an impure substance. That means a solid solution of alpha being in equilibrium with a solid solution of gamma. It's no longer the case that G alpha equals G gamma, which defines equilibrium. Just to remind you, from yesterday, we derived the theory for the free energy curve for an atomic solution. Okay? So when I mix up the atoms, this gives me the free energy of mixing here, the difference. Right? This is the mechanical mixture, and this is the atomic solid solution. So the free energy curve for a binary solution, no longer pure, so we have A and B here, will be given by a curve which looks something like this. Okay? Now, supposing now I have another phase, then I will have another free energy curve here, and it's not clear how we define equilibrium between alpha and gamma. Okay? You will have two free energy curves. We've got X, G, then I might have alpha and gamma. Now, this point here, where the two phases have the same free energy, is not equilibrium. Okay? How do we define equilibrium for solution? This is now a solution of A and B, and this is now a solution of A and B in a different crystal structure. Now, we need to think about taking a solution and saying what is the contribution to the free energy of that solution from the A atoms, and what is the contribution to that solution from the B atoms. So if I look again at the free energy curve for, say, the alpha solid solution, if I have that composition, then that is the free energy of that solution. If if I now decide to draw a tangent here, the tangent is at this point here, this is the composition of the solution, then the intercept here is mu A, and this is simply the amount of A, and this is mu B here. Now why have I drawn a tangent? Well, by drawing this tangent, I can write G simply as the weighted average of mu A and mu B. Okay? So I can write this equation here, that the free energy of the solution comes from mu A times the concentration of A and mu B times the concentration of B. Okay? So there's nothing complicated here. This is just the equation of that straight line. Okay? We haven't done anything complicated. I'm just writing GA is equal to mu A times the concentration of A plus mu B times the concentration of B. Okay. So this is the equation. But the interesting thing about this equation, which is really important, okay, you need to understand this, is that this term depends only on A and this term depends only on B. So what we've done is we've divided the free energy of the solution into a part due to the A atom and a part due to the B atoms. So this is the free energy of B atoms in a solution of composition X, and the free energy of A atoms in a solution of composition X. This is the concentration of A and this is the concentration of B. So I can now say that this much of the free energy of this solution comes from the A atoms and this much comes from the B atoms. And in thermodynamics, we say that mu A is the chemical potential of the A atoms and mu B is the chemical potential of the B atoms. That means the free energy of A atoms in a solution of a particular composition. Okay. Chemical potential of A atoms and chemical potential of B atoms. So, equilibrium now between two phases is when the chemical potential of A in alpha is the same as the chemical potential of A in gamma. Because if the free energy of an A atom in alpha is the same as the free energy of an A atom in gamma, there is no tendency for diffusion. Okay. So equilibrium is simply defined by writing these equations. If I have 20 different components, then I write 20 different equations. So now, for equilibrium between solutions, it is when the chemical potential is uniform, you have equilibrium. Okay. And on a diagram, you do it like this. I have got two of these curves here, two phases. If I draw a tangent which is common to both of these curves, then this gives me the equilibrium composition of alpha, equilibrium composition of gamma. And if I extrapolate this tangent here, you can see that mu B is the same in alpha and gamma, and mu A is the same in alpha and gamma. So they are at equilibrium. If the free energy of an A atom is the same in alpha and in gamma, then there is equilibrium. Yeah? Now notice that the compositions of alpha and gamma are different. Alpha has a different chemical composition to gamma. And still they are at equilibrium. Okay? So you take salty water and ice. They have different chemical compositions, but they are in equilibrium. There is no tendency for salt to diffuse from the water into the ice. So this says that Fick's law of diffusion is wrong. Yeah? Because Fick's law of diffusion says if you have a concentration gradient, you get diffusion. That is wrong. There is actually no free energy gradient here, because the chemical potential of A atoms in alpha is the same as chemical potential of A in gamma. We should really think about diffusion as being driven by free energy gradients, not composition gradients. Is everybody happy with that? Okay, so equilibrium is straightforward to define, that the chemical potential must be uniform throughout your system. It doesn't matter how many components you have, how many different phases you have. And if if I go to a ternary system, oh, this is just to say that the compositions are not equal. It's the chemical potentials which are equal. This is just to show you ice in seawater. Okay? They are in equilibrium, even though they have different chemical compositions. Ice is much more pure than seawater. It has very little salt in it. So if you are ever stuck in a raft in the sea and you can't drink seawater, just grab hold of some ice and melt it. Now, if we have three components, then the free energy surfaces that we have here, free energy curves here, they become free energy surfaces. So this is now a surface in 3 dimensions. And equilibrium is obtained by drawing a tangent plane. And where that tangent plane touches both of the surfaces, okay, that defines the equilibrium composition of gamma and equilibrium composition of alpha. So you can see that the chemical potential of iron is the same in alpha and gamma, chemical potential of carbon is the same in alpha and gamma, and the chemical potential of X is the same in alpha and gamma. So there's nothing different here from the binary case. I can't draw a diagram if I have 4 elements, but the equations are the same. Now, all the theory that I've told you about these free energy curves is actually too simple. All the curves are symmetrical about a concentration of 0.5, 50% A, 50% B. The real free energy curves are more complicated when you measure them. Okay? And if we try to develop theory for complicated curves, then the equations become incredibly complicated. Okay? So we don't want that. We want to be able to calculate phase diagrams for 20 different elements and 20 different phases existing at the same time. So people throughout the world, the pioneers in the subject are Hillard and Kaufman and Kubashevsky. They developed a set of equations which are empirical equations. Okay? So they are polynomial equations. And those equations are designed in such a way that they can deal with very complicated systems. Okay? So I'll explain that now. So instead of writing the free energy rigorously in terms of the entropies, equations, and so on, the best theory we have, we write it as a polynomial like this. So this is now the free energy of mixing. This is the concentration of A and B. This is a binary solution. And we have a polynomial equation here, where this is A coefficient, and this is the difference between XA and XB, and we have an exponent here. And if I expand this equation, then I have this term here, which is exactly the term I showed you yesterday for the enthalpy of mixing. So this is a rigorous term. It is based on physics. But then I add some further empirical terms. XA, XB times another constant times the difference here. And that allows me to have asymmetry in the free energy curve. And I can continue adding terms to make it more and more complicated if I need. If I then go to a ternary system, ABC, I can add further terms. Don't worry about this equation. The thing that I want you to notice is that supposing that we have derived values of these coefficients, okay? And then somebody does an experiment which says that, look, I've got a more accurate value of this. Then these values don't need to be changed. The way the equation is designed is that if I alter one coefficient, I don't need to alter the other coefficient. Okay? So imagine that we have a massive thermodynamic database. If somebody derives a more accurate value of one coefficient, it is very painful to modify everything in the database. So these equations are designed so that if you change one of these coefficients, it doesn't affect any other coefficient. So notice that if I set the concentration of one element to 0, then this becomes a binary equation of, oops, becomes this again. Okay? So the ternary automatically becomes binary if I set the concentration of one solute to 0. So they are very clever equations, and I can make them more and more complicated to represent more and more complex solutions. And all of this is incorporated into thermodynamic databases which you can buy, yeah, and use to do phase diagram calculations. So almost all major industry now uses phase diagram calculations based on these methods. Here is an example calculation for the iron chromium nickel system. So this is a cross section of a ternary phase diagram at a constant temperature. And there are many different phases and equilibria between many different phases. And this is what I would call a simple phase diagram. You know, we have only 3 elements in it, but you can have 20 different elements. You won't be able to draw a diagram, but you'll get the equilibrium compositions, you'll get the equilibrium phase fractions from the calculations. Now, one of the problems with all of these methods is that because they use polynomial equations, when we try to do calculations in a region where experimental data don't exist, then you might actually be extrapolating incorrectly. Okay? If you use an empirical equation, then you can't be sure that when you do calculations outside of the domain of experimental data, you will have accurate results. So this is the like the iron carbon phase diagram. Very often for bainite and for martensite, we need to do calculations at low temperatures where thermodynamic data may not exist. Okay? Measurements may not exist. You can't do a proper thermodynamic measurement of martensite because it's not equilibrium phase. Yeah? It doesn't appear on the phase diagram. So if I want to extrapolate this phase boundary down to low temperatures, do I extrapolate like this or do I extrapolate as a straight line? Yeah? So you have to be careful when using these computer programs if you are working far away from the domain where experimental data exists. And there are methods which are more complicated. Okay, so let me just show you. First of all, I'll show you the danger of extrapolating. Okay? So this is Wittgenstein ferrite. And if I calculate the growth rate of that Wittgenstein ferrite, I can get many different answers depending on which thermodynamic model I use. Yeah? So you can see here, the difference is by an order of magnitude in the growth rate. Okay? So although you can buy the software to do phase diagram calculations, you need to understand when you're doing calculations which may not be correct. Okay. Now, in order to extrapolate, you need to use proper physics rather than polynomial equations. And that physics does exist. You know, this is the simplest kind of solution where we only have entropy of mixing, but there's no change in bond energy. Then we have the regular solution model where we have an entropy of mixing and an enthalpy of mixing. And this is the most rigorous kind of model where the calculation of the entropy of mixing and the enthalpy of mixing is very, very good. But the equations become very complicated, and that's the reason why they are not implemented in commercial software, which is very good for doing general calculations. Okay? So just to give you an idea, this comes from the quasi-chemical theory, and you can see this equation is very complicated, and this is just for a binary solution. And this term itself has a lot of meaning. Okay? And in fact, inside this term, you have the interaction energy between atoms. Okay? So if I take two A atoms, put them an infinite distance apart, and I bring them closer and closer together, then the energy changes in this way. And this is what we define as the binding energy between two A atoms. And we need this kind of information to use these equations. So I don't want you to worry about the details, The only point I'm trying to make is that if you're extrapolating far away from the region where data exists, you need to be careful. Now, sometimes these data, the binding energies, are not available experimentally, but you need them to do the proper calculations. So how do we proceed? Sometimes the experiment may not actually be possible. Well, we then start to use electron theory. Right? Now, electron theory allows you to calculate bond energies, elastic moduli, the crystal structure. So you can say, okay, I want iron in the diamond crystal structure. What is the cohesive energy of that? You can do that calculation even though iron doesn't exist in the diamond crystal structure. Now, the big limitation of electron theory is that you can only deal with small numbers of atoms. So, for example, you can deal with ordered compounds. But if you want a disordered solid solution, then maybe the size of the cell becomes so large that it's impossible to do the calculation. And you know, the problem won't disappear if you have more powerful computers. You will always have a limitation on the number of atoms that you can treat. Okay. And when you're looking at differences between the free energies of alpha and gamma, the inaccuracy might be larger than when you're calculating for a single phase. So, in my opinion, phase diagram calculations using first principles method are simply not accurate enough for material science. Yes? You know, if you do a calculation for the phase diagram of iron, it still isn't accurate enough compared with what we know is the correct phase diagram. Okay. So you have to use this method the problem that you use this method for must be very carefully defined so that you can get the result from small numbers of atoms. So let me give you one example. This is the unit cell of ferrite. The body centered cubic. You can see the iron atoms. If I put a carbon atom inside that unit cell, then it will sit along the edge of the cell.